Okay, so when you think about the very heart of our galaxy, what comes to mind? For most of us, it's Sagittarius A star, right? The supermassive black hole that we've been told holds the entire Milky Way together. For decades, that's just been a fact of astronomy.
And, I mean, why would we doubt it? Back in 2022, the Event Horizon Telescope gave us this absolutely mind-blowing image. You know the one, that dark central void surrounded by a ring of glowing hot gas. It really felt like case closed. Definitive proof.
But what if I told you that some brand new data is telling a completely different story? A story that seriously challenges everything we thought we knew. What if that thing at the center of our galaxy isn't a black hole at all?
So, where does this wild idea come from? Well, the mystery really kicks off with a huge contradiction that was uncovered by the European Space Agency's Gaia mission. See, when you look at the big picture of our galaxy, the data just doesn't quite line up with our standard black hole model.
Okay, so here's the puzzle in a nutshell. On one hand, you've got stars really close to the galactic center, like one called S2, that are whipping around a massive object at insane speeds. And that fits perfectly. It's exactly what a black hole's gravity would do. But on the other hand, if you look at the stars at the very edge of the galaxy, they're slowing down way more than they should be. Our standard models say a giant halo of dark matter should be out there, keeping them moving fast. The big problem is there's no single theory that can explain both of these things at the same time. It's a major contradiction.
And it's this contradiction that's really opened the door for a pretty radical new idea. A recent paper is proposing that maybe, just maybe, the object at our galaxy's center isn't a black hole, but something else. A super dense core made of a very particular kind of dark matter. This whole theory is built on these fundamental particles called fermions. And to put it simply, fermions are what everything is made of. I mean, you, me, this planet, the stars, we're all just made of fermions. They're like the universe's fundamental solid Lego bricks. And these little building blocks, they have to follow a very strict quantum rule. It's called the Pauli exclusion principle. The best way to think about it is like trying to pack solid blocks into a steel box. Sooner or later, you just run out of room, right? You can't just keep forcing more in. Well, fermions are the same way. They refuse to occupy the same space, so when you try to squeeze them together, they push back hard.
And this pushback is what could create this core. So imagine the immense crush of gravity from 4 million suns worth of these dark matter particles, all pulling inward. As they get squeezed tighter and tighter, that quantum pushback force, what scientists call degeneracy pressure, gets unbelievably powerful. Eventually, the inward pull of gravity and the outward quantum push reach a perfect stalemate. The collapse just stops dead in its tracks, forming a stable, mind-bogglingly dense object that never actually becomes a singularity.
Okay, so that's the theory. How does it actually hold up? Well, the real beauty of this idea is how it seems to solve both of our galactic puzzles with one single, surprisingly elegant explanation. First, let's just remember the sheer scale we're dealing with here. No matter what model you're using, a black hole or this new core, it has to account for the gravitational pull of 4 million suns, all packed into the galactic center. So, what about those super fast stars near the center? Well, there's a classic rule in physics that says if you're orbiting a big sphere, its gravity acts like all its mass is packed into a single point right in the middle. And since these stars orbit outside the proposed core, they would feel its gravity in exactly the same way they'd feel a black hole's. From the star's perspective, there's no difference. The orbits match the predictions perfectly. So, puzzle number 1, solved. And the outer stars? Instead of that huge, sprawling dark matter halo we always thought was there, this model suggests a much more compact one that pretty much just ends where the galaxy does. And that would explain exactly why the outer stars slow down so much. The gravitational tug from the dark matter just kind of drops off a cliff. They start moving more like planets around a sun, which, believe it or not, is exactly what the new Gaia data is showing us. Okay, but that leaves one absolutely massive question, right? The elephant in the room. What about the photo? If it's not a black hole, why in the world does it look exactly like one? The logic seemed totally solid. I mean, a black hole has an event horizon, that point of no return where not even light can escape. So when you see a dark shadow silhouetted against all that bright gas, the obvious conclusion is you're looking at the event horizon. But this is where things get really clever. A black hole creates a true shadow by literally swallowing light. The fermionic core, though, it does something different.
With 4 million suns of mass packed into that tiny space, its gravity is still so intense that it massively bends the path of any light that travels near it. This process, known as gravitational lensing, essentially deflects light away from our line of sight, creating a visual void, an illusion that looks identical to a real shadow.
And look, this isn't just a guess. The research team ran some seriously advanced computer simulations. They modeled this dark matter core, surrounded it with plasma, just like in real life, and then they tracked where the light went. And the final image they got? It was practically identical to the one from the Event Horizon Telescope. It turns out the photo only confirms there's something incredibly massive there. It doesn't actually confirm it has an event horizon.
So if both the black hole model and the quantum core model can explain the star orbits and the photo, how on earth do we ever find out the truth? Well, it all comes down to one single, decisive feature that can settle this once and for all.
And that feature is called the photon ring. According to general relativity, right on the edge of a true black hole's event horizon, there must be a razor-thin, super bright ring of light that's literally trapped in a perfect circular orbit. A real black hole has to have one. But a fermionic core, because its mass is spread out and not a single point, just doesn't have a steep enough gravitational cliff to trap light like that. It cannot have a photon ring. It's a clear, testable difference.
And here's the best part. This test is happening right now. Scientists are using the gravity interferometer down in Chile, an instrument powerful enough to actually see this feature, and they are scanning the edge of Sagittarius A star looking specifically for this signature. The presence or absence of a photon ring will finally settle the debate.
You know, the results are going to be profound either way. Are we about to get the final confirmation of one of the most extreme objects predicted by physics? Or are we about to discover that the heart of our own galaxy is made of something even weirder, a colossal quantum object held in perfect, delicate balance? All we can do is wait and see.